Good afternoon. My name is Krishna Naishadham. Actually, I'm also affiliated with the Georgia Institute of Technology in Atlanta. And my co-authors, you can see. So I'm especially grateful to Elena Bekyarova, who is the chemist in our group, So she's the one behind all these exciting sensors that we develop. So today I'm going to talk about ozone sensing and our approach based on carbon nanotube based films. So basically I'll give a very brief introduction to nanotechnology based sensors, and then the particular application that we are targeting is air quality monitoring for asthma patients. And we'll go into some of the sensor design details and measurements and then conclude. So carbon nanotubes are, nanomaterials are available in various different forms. The initial raw material is graphite, or diamond is another version of graphite. And nanotubes, and they are basically two-dimensional sheets rolled into the form of tubes. They are available as single-wall nanotubes or multi-wall nanotubes. And fullerenes is in the form of a pentagonal lattice, as you can see here. And one of the most promising nanomaterials is graphene, which is a single atom thick planar layer of carbon atoms in a honeycomb lattice. And you can think of CNT as basically a configurationally, it's a two-dimensional cylinder formed from graphene. And so what we do is we have these nanotubes in raw form, and we mix it in an appropriate solvent, sonicate it, agitate it, and then make an ink and deposit this ink on interdigitated electrodes. So we are in the process of making a sensor array consisting of films specialized to different gases. This is just an illustration. It does not mean that we are making sensors for all these gases, but we have capability to develop whatever atmospheric pollutants are. So what is the advantage? Why is nanotubes? They are highly sensitive because they can be functionalized to different materials, so they have high specificity, and they are low power consumption, a fast response time, few minutes, typical, uninterrupted use. You do not have to, you can operate them at room temperature if you are able to tolerate a little slower response. Ease of integration with electronic devices and wireless devices like mobile phones. So we are making a smartphone based sensor for IoT kind of application. So this is one of the first nanotube sensors developed at MIT. And basically you have silicon dioxide passivating layer, and you have interdigitated electrodes, gold electrodes. And these are, the nanotubes are deposited across the gaps between the electrodes. So they are aligned in the direction of the electric field between the electrodes. And you can see these string-like materials, which are nanotubes. So because they are specifically tailored to this structure, they change the capacitance or resistance in a very sensitive manner, and that is the advantage of nanotubes. So in this particular sensor, this parts per trillion detection of a hazardous material called serine. Okay, serine, precursor to serine, that's what they developed in this. So there are a lot of uses, environmental air quality monitoring, patient personalized health monitoring, like glucose sensors and so on. So this is developed by my co-author, Elena Bekyarova. So this is an ammonia sensor. If you do not have functionalization, basically raw nanotubes, you get a response like this, which is not very sensitive. But once you functionalize it with a polymer, which is specific to ammonia detection, then you get a really fast response. And when you remove the source of gas, you get this reversal, okay? that is very specific to nanotubes. So the sensor goes back to baseline. So you can cycle this many times. That is why it can last for a long time. It's typically 6 months to a year. And so the response is about, sorry, something. So the response here is at least 20% higher than here. So functionalization has benefit. And as an application, this is some kind of device, developed at University of California, Berkeley, based on nanotubes. So those are the sensors. This is the flexible electronics which connect with the sensors for data logging. And so it's a smart wristband, and you can use these sensors to detect, for example, environmental pollutants such as ozone and particulate matter. And you can show, because once you have electronic signal, you can do anything with it. Here you have connected this to a smartphone, and you are showing different statistics like concentration, etc., or alert. There is a danger here, air quality is very bad. So if it is a patient, like an asthma patient wearing this device, he or she can make a decision based on this alert. And you can even show a bar chart like this, with different pollutants. So this is the application that we are targeting. So what we have now, it comes to our sensor. So what we have is a pair of interdigitated electrodes on alumina substrate. This whole size of the substrate is about 7 millimeters squared. And we have platinum electrodes screen printed on this. So we take the base CNTs, purify them with nitric acid, and this leaves with carboxylic acid functional groups. And those functional groups are covalently modified with this chemical ODA to improve the sensitivity to ozone. So in other words, this particular chemical gives the sensitivity to ozone. And these are some of the statistics, some of the mixing ratios, 1 to 3, and so on. So this is the solvent that we used. So the CNTs, ODA CNTs are dispersed in the solvent and prepared into ink. And then this ink is sprayed onto the electrodes by spray coating. Some of the physical characteristics, this is the SEM image of the nanotubes. And you can see these white, the white, almost like isolated islands. Those are the ODA functionalization molecules. And these strings here are the nanotubes. So the morphology indicates a highly porous network of fibers, carbon fiber, CNT fibers, and functionalized with these molecules. And we did a thermogravimetric analysis to figure out the mass loss, so at what temperature the material becomes ineffective, because that's a very good parameter for the sensor operation. So we found that till about 200 degrees, the material is pretty stable. Afterwards, it degrades. And we did some spectroscopy also. I'm not an expert in chemistry, so these are all comments from my co-author, Dr. Bekyarova. Basically, this spectroscopy shows the existence of functional groups, oxygen functional groups, and also the electronic structure of the functionalization is preserved. Okay. This is the gas measurement setup. We collaborated with Politecnico di Torino in Italy for this with Professor Jean-Marc Tulliani. So this is the lab he has. It's a very nice setup. He has dry air and different gas supplies. And so what we have is an ozone source, which is an ultraviolet lamp. So the dry air passes through this, and the ultraviolet lamp ionizes the air and creates ozone. And the ozone is inserted in this gas tube, and our sensor is standing there, and it is exposed to ozone, and this is the exhaust. So we can measure 200 to 500 ppb, And we also have a heater. We need to heat it slightly to 75 degrees to make the sensor response fast. So we have a heater next to the sensor, so we flow this ozone at this rate, and we are observing the response by measuring the impedance between the electrodes at 1 kilohertz using a benchtop impedance meter. So these are the results. First, we study the temperature sensitivity. At room temperature, you get this response, right? The black line, it is very, very slow, very slow. And when we remove the gas and put in dry air, it tries to go back up. So this is our baseline, and then ozone, and then it tries to go back up, but it is very, very slow. So then we started looking at temperature, where if we can increase this response, speed of the response by heating. At 50 degrees, you get this blue line, still very slow. At 75 degrees, you get this line, the red line, which is really good. So you get the best sensitivity at 75, and greater than 75 at 100 degrees. It seems like the material is not functioning. So that is the breakdown. So the best temperature is 75 degrees. So we heat the sensor to 75 to make the response only 15 minutes response time compared to 37 minutes at room temperature. Now these are the cycling. So here I cycle from 200 parts per billion, and then remove the gas source, remove ozone, it goes up. So the baseline is here. When you have the ozone, because it's an oxidizing agent, therefore the impedance will drop. In other words, the conductance will decrease, or the resistance will increase. Sorry, I said the other way. Conductance increases, the resistance decreases. So the impedance will go down with ozone, and then when you remove the ozone, it comes back up. So we cycle it from 200 to 300 ppb. So you see that it is very, very repeatable, and you get a really nice fast response of the order of only 15 minutes. And 1 minute, okay. Humidity, this is a big factor in environmental sensing. So when we subject the ozone with humidity, we see that there is only 16% change in the response. That means it is not compared, this is a very good figure compared to state-of-the-art existing MOS, metal oxide sensors. So this is a really good result. So the sensitivity to humidity is small. However, sensitivity to nitrogen dioxide was quite high. It was 41%. So what we did is a cross-sensitivity analysis of different molecules, different substances. We found that methane, carbon dioxide, and ammonia, they had no cross-sensitivity. They had no interference. But the biggest contributor was nitrogen dioxide, and humidity was marginal, so it can be calibrated out. But so in conclusion, this sensor is sensitive to ozone. It gives very good response, but it is also sensitive to nitrogen dioxide. So that's not so good. So I'll conclude. Basically, we designed ozone sensors using functionalized single-wall nanotubes. This is the functional group that we attached to the nanotubes. We characterized the sensors by measuring the impedance at 1 kilohertz. We got really good response, 60% change for 200 parts per billion ozone at 75 degrees centigrade. Cross sensitivity was small for humidity, but reasonably large for nitrogen dioxide. And there were many gases which are found in the ambient environment, like carbon dioxide, ammonia, which were not cross sensitive too. Thank you very much.